connection. So it will be about the design of connection between steel members. So this is overview of the topic we have today. So we will have introduction to the connection design, design of bolted connection, and design of bolt groups. So we will be mainly talking about the bolted connection, which includes bolts. And for the welded connection, you maybe have a read on it later if you need. But the course will focus only on the bolted connection. And we will be using the Strutural standard AS4100. And this is the two reference book if you want to have a look on the connection part in this books. Okay, so let's start with the introduction to the connection design or the bolted connection design. Again, we have bolted and welded, but we are focusing on bolted. So the connection elements consist of connection components like cleats, gusset plates, brackets, connecting plates, and the connector or fasteners like bolts, pins, or welds. The connection in a structure shall be proportional to be consistent with the assumption made in the analysis. So when you design the connection, it need to be consistent with the assignment, like the assumption. Like for example, if you designing a frame, so you have a rafter and column. So if you consider the connection between the column and rafter rigid, so you need to design a rigid connection here. Okay, another option, if you consider the connection between the rafter and column as pin joint, so you need to design a pin connection here. So based on your assumption, the final design of the connection depend on just. The connection are needed to transfer the forces from the members to footing, for example, transfer forces from non-structural building element to the structure itself, join the members together in trusses and lattice girders, join blades together to form built-up members, join beam to beams, and join beams and trusses, bracing, and so on to columns in structure frame, similar to this one. So just quickly here, if this is a frame, so there will be a connection between this column and this rafter, and this column and this rafter. So we have at least one connection here and another connection here. Okay, also connection between column and foundation, similar to here. So for example, we have footing one or connection one, beam connection, or hinged footing. And the other one also is hinged footing. So these are some example of the connection we may have in steel structures. Typical connection in steelwork construction, shop connection, and fixtures. So we have some like fixed example of the connection or standard details of the connection. We have direct connection between members like welded truss, welded or bolted subframes, brackets and fixture, and side connection or splices like column beam splices, beam to beam connection, beam to column connection, column base to footing connection. Usually most of the connection bolted because bolted is speedy in erection compared to welding. And these are some example of the connections. Like for this example here, trust connection. So all the members are connected using a gusset plate. So we have members here, member 1, member 2, member 3, member 4, member 5. So 5 members are connected. So in the structure analysis or in structure, this connection is represented like that. So you have member 1, 2, 3, 4, 5, and this connection is our connection here. Example number 2, we have like base plate connection. So if this is our footing, so we have a plate and there is some bolts here or connection here to connect the column to the footing. Okay, and here number 3 and number 4 are column splices or column splice and beam splice. Okay, column splice and beam splice because sometimes if you have a like long column, so you might need to connect this column because you have two pieces of it. So you connect using this type of connection, which is called splice. Okay. Here also similarly for the beam or for the rafter, if you have long rafter, so you need to make a splice. And here, two example of beam to beam, beam to beam and beam to column. So this is our beam and you need to connect another beam here, for example. So this is the connection. Here, if you have a column and you want to connect a beam, so this is a beam column connection and this is a bracket connection. So this is a column and a corbel or a cantilever. So you have some loads here. So this is how to connect this corbel to the column. All of these are some few example of the connection, steel connection, bolted connection. And the third point is connection by fastener type. So some classification according to the fastener type. So according to the fastener type, the connection can be classified into 3 types. Welded connection. We have or 3 types of welding: butt welds, fillet welds, or compound, like mix of butt and fillet welds, or bolted connections using snag tied bolting, denoted by /S, or controlled post tension bolting, or working by bearing contact, denoted by TB. So there is several types of bolted connection depending on how to apply the forces to tie the connection, or sorry, to tie the bolts. And there is also another type of connection working by friction grip, denoted by /TF. The third type is pin and pin connection, which using rivets, seldom use or old-fashioned connection. So this is not very common now. So we have between welded and bolted connection. Bolted connection usually preferred due to low sensitivity to unavoidable dimension inaccuracy in fabrication, shop detailing, or documentation. So low sensitivity to errors, simplicity and speed of installation and erection, low demand for skills of workers, doesn't need very high skilled workers, relatively light and portable tools compared to welding. So these are some pros of using the bolt connection compared to welding connection. The design principle for bolted connection, typically material costs represent only about 25 to 50% of overall cost of the steel work. So the connection is between 25% 50% of the cost, depending on the type of the connection and what is the load need to transfer between the two connected members. Connection consists of a small percentage of total steel mass, but plays a prominent part in the economy of steel work. The economics of steel structure is highly dependent on the type of the joint rather than the size of the member. So again, the economics are behind the connection depend on the type of the connection rather than the size of the member. Making connection and details is labor intensive. Many large and small pieces must be manufactured and fitted within the specified tolerance. The design principle for connection are designed for strength or designed for fatigue resistance, designed for serviceability, and designed for economy. So 5 principle for connection design. For strength, direct force transfer bus. So need to design how the force transfer between the connected member, avoid of any stress concentration at the connection, adequate capacity to transfer the forces involved, otherwise the connection will fail. Design for fatigue resistance, avoidance of notches, carefully design of welded joints. For self-stability, we need to avoid feature causing the collection of water. For example, you need to make sure that any connection you design doesn't collect or cause collection of rainwater, for example. Ease of application of protective coatings to prevent the erosion. Absence of yielding under working load. So we need to make sure that the connection will not yield under the working load or the design load. Design for economy, simplicity, easy to fabricate, erect, and maximize the repetition. So for the bolted connection, it is easy to repeat and make like modular design. Minimum number of elements in the connection. Reduction of the number of members meeting at the connection. Okay, like for example, don't make all the members like meet at same point because this connection will be too complicated to design. The fundamental of design consideration, firstly, strengths. 4 elements in the design model for assessing the strengths of the connection. Strengths of bolts or fasteners. Strengths of the connection components. Like for example, if you have 2 members connected, so you have the strength of the bolts itself, strength of the members connected, and strength of connected members in the vicinity of the connection, strength of the supporting member in the vicinity of the connection. Okay, so all this need to be checked. Like for example, here's this a clarification again. So we have the fastener, the connected member, and this is the column supporting member, number 4, and this is the connection components. So this is number 2, and actually this is number 3. So we have the connection components, which is the plate here. This is the blade that connect the rafter to the column. We have the connected member, which is the beam, and we have the supporting member, which is the column. So this is our column, this is our beam. So we have fastener, So the strength of fastener, strength of the beam, strength of the plate connecting, and strength of the column. So these four strengths need to be checked to make sure that the connection is safe and stable. In a steel structure, the connection or joint should be probably designed according to the design method. For example, if the framework for an office building will not be exposed to view, all bolted connection can be chosen purely due to the need for rapid erection. The frame will thus be of simple construction, possibly braced by lift core. So if the bolted connection will not be exposed to view, so it is better to choose the bolted connection. If the connection will be viewed by people or user of the building, so it is better to use welding. In contrast, if the steel work will be exposed to view, the choice may be braced framework with pin type connection or rigid frame with welded connection. The choice of the connection type also related to the types of frame. So, for example, we have rigid frames work or simple framework or semi-rigid framework. So for rigid framework, you need to have rigid connection between the members, like all this connection between the member are rigid connection. But for simple framework, all this connection are pin connection. Okay, so for rigid connection, welded connection or non-slip bolted connection are preferable. Heavy bolted end plate are preferable. Assume to have sufficient stiffness to maintain the original angles between the members during load. Because as you know, when you design a rigid connection, the angle between the member need to remain the same after loading. So that's why we need sufficient stiffness of the connection. Joint deformation shall have no significant influence on the distribution of action effects, nor on the overall deformation of the building. So we need also to make sure that there is no joint deformation have significant influence or significant effect on the distribution of forces. So this means that we don't allow deformation of this or high deformation of this connection. Simple framework, which you have simple connection or pin connection. So simple connection, flexible end plate connection, slippage permitted. So in this type of connection, slippage is permitted on web and flange cleats. We are in this connection capable of deforming, so deformation is allowed. To provide rotation at the connection, assuming the ends of the connected member don't develop a restraining bending moment. So there is no end moment due to due to restraint at the ends. Reaction shear forces at eccentricity shall be considered. So we need to consider some eccentricity at the connection. For semi-rigid framework, a semi-rigid framework connection designed to control rotational deflection and deformation. So that is the connection in these members are something between pin and rigid connection. Not pure pin or not pure rigid, something between. So it allow a required amount of rotation and deformation. So it is allowed to deform and rotate by certain amount or required amount. Behaves somewhere between rigid and simple connection. So this type is between simple and rigid connection. In this figure, some examples of beam column connection. So it's between column and beam. So for the first line or the first three images, we are simple connection. So simple connections just mean that no moment transfer between the two members. This is the structure definition. So this is an example here. Here also another example. Here another example. So as you can see here, web only connected and flanges are not connected. So this is the main difference. We only connect the web, not the flange. If we look at the second example from D to G, we have all of them are rigid connection. So we may have here plate here, and as you can see, here the flange are connected. Here is welding. Okay, here is also welding. Here is welding. But the main thing here that web and flanges are connected to the member. Okay, so the next is the design action of the connection according to the standard. So the standard AS4100 clause 9.14 for the connection. So you can find the connection design in section 9. So AS4100 requires the connection to be designed for forces larger than member design action. When the member size is larger than the required of the strength design, connection design action must not be less than certain specified minimum. Okay, the following table summarize the requirement of the standard. So in this table, we just have a look on the requirement and then we will design the connection in details in the next part. So here, for tension member, the splice and end connection, the minimum action to be designed on is 0.3 phi nt, where nt is the nominal member tension capacity of the member. So if you are designing a connection of member under tension, so if you design something here, this member is under tension, so you need to design this connection, sorry, for 0.3 or 30% of the nominated member force. Okay, for compression member, for example, also 0.3 or 30% of the member capacity. For flexure members, like beams and so on, need to design for 0.3 phi MB, or where MB is the member moment capacity. So these are summary of what is the minimum required design forces for each type of connection. Okay, so now if we go to section 2, so we have the design of the bolted connection. So bolted connection, firstly, the simple framework or pin connection. Characteristic of simple connection commonly used in simple construction: minimal rotation restraint to member ends, transmit only shear, moment is nominal due to eccentricity. So this is connection or simple connection transmit only shear. So this is the main criteria. The moment is minimal due to eccentricity only. So there is no moment, or moment is almost equal to zero in this type of connection. The commonly used simple connection are web to flange cleat or angle cleat, flexible end plates, fin plate or website plates, bin type connection. So these are 4 type of connection, and we can have a look here on these types. So for example, this one here, as you can see here. So this is called double angle web cleat. So this connection is connecting the web of this beam to this beam. Okay, another type of connection is flexible end plates. So flexible end plate, this is the flexible end plate. Connecting this beam to this beam. Here is the fin plate. So connecting this beam to this beam. And this is the fin plate. Okay, here and here, these two are column splices. Here is bracing connection. So this all are types of simple connection that only transfer shear, but doesn't transfer moments because the moment is minimum or almost zero in the simple type connection. Do you have any question, guys?
No, sir.
Yeah, Ahmed, I'm just wondering why
Thanks,
would you need to transfer the shear, like have those braces there if there's no moment?
It is not like that. I mean, like when, for example, if you have a beam
Yeah.
like this and column like this, okay? So you need to connect this beam to this column. So if there is loads here, so the
Yep.
connection here can be 2 types of connection, okay? Can be rigid or bend or simple.
Yep.
Okay, depend on the type. So if we put a support here, so this connection we can make it bend. So if it is bend, this
Yep.
means that the loads on this beam will be transferred. Part of the load will go to the left support, right?
Yep.
And the other part will go to the other support, right?
Yep.
So where this load will go to the column.
Yep.
Or will be transferred to the column. So this is called shear because it is vertical or like parallel to the section of the beam.
Yep.
So that's why it's called transfer shear. And because the moment here at this point in this case is zero, so this connection will not transfer moment,
Yep.
right? So when you design, like if this is the section of the beam, and this is the section of the column, right? So you just need to connect only the web. There is no need to connect the flange.
Yep.
Why there is no need to connect this flange? Because there is no moment to be transferred between this beam and this column, right?
Yep.
Another example, if this cantilever without support here, and this is the column. So there will be moment transfer from the cantilever to the column. So the connection here need to be rigid connection. So when you create this connection, why? You ask why? Or you don't ask why?
Oh yeah, no. I guess my question, if you had, rather than a beam there, like if that was the rafter, say, so it's connected to another beam, could you then have a pin connection, or would it have to be a rigid connection?
Yeah, if beam to beam can be pin connection.
Okay.
Yeah,
And,
but it depends on the supports the other side as well. Like that's what I mentioned here.
yeah,
So the difference here is
yeah,
if you put a support here, so there will be no moment at this end here, connection one.
yeah, yeah,
But if there is no support here, so there will be moment at connection one.
yeah. So say if that second one,
Yeah, so second one here can be
yeah,
bent.
yeah,
No need to be rigid, but
yeah,
first one here need to be rigid.
yeah. Okay. Yep. Thanks.
So it depends on the condition of the connection. What is the connection is used for?
Yep. Okay.
Yeah. Okay, so good question. Thank you, William. So now for the bolted connection or rigid framework. So let's look at the rigid connection. So the rigid connection, characteristic of rigid connection commonly used in rigid framework. So for frames again. So if there's a frame, so the connection here, both of them may be or commonly need to be rigid connection. Maximum rotational restraint to the member ends. So you need to have rotational restraint at both ends here. This connection transmit shear and moment. That's why you need to connect the flange, the two flanges and web. Commonly used rigid connection in the moment connection or the moment connection, this type, end plate moment connection. So this is two types of the end plate moment connection. One of them is flush. So as you can see here, the connection plate end with the member or extended. So the connection plate is a bit bigger here. So let's say this is our column. So the beam is supported to this column. Okay, so here this connection will be designed for a shear force and also a moment. That's why we connect the web and the two flanges. Okay. Another type of this type of connection or the moment connection is hinged connection. So apex connection, one of the examples. So what is the apex connection? If you have a bed sheet frame like this, so the connection on top, if this beam, this is our rafter here. So this connection is called apex connection, like that. And this connection will transfer moment and shear. That's why it need to be rigid connection. Another connection also is the rigid connection. Eaves connection. So similar to here. So you need also here to have a rigid connection. Why sometimes need haunches here? The haunch here or here because of the moment. So for example, if I draw the moment here, so you will have larger moments at this section here. So this is M max. So because the moment here at this point is larger than the other side of the beam, so that's why we need the haunch. What is the use of this haunch? The use of this haunch is that you have enlarged depths at this section. So you have bigger section. Here as well, at this section here, you have also bigger moment. That's why you have enlarged depths. So these haunches are mainly for increasing the section to resist the high moment in this section or in this area. Types of bolts and installation, because in the market you have some different type of bolts based on the strength and the type of installation. So categories of bolts used in steel construction. So we have class 4.6, class 8.8, and class 8.8, 10.9, and 12.9. So the maximum is 12.9 and the minimum is 4.6. So 4.6 is commercial bolts, low carbon steel, like grade 250 steel. So this is the minimum strength generally used, suitable only for snug tight installation. So it is only for snug tight installation. That's why it is 4.6 slash S.
Hello, can anyone hear me?
Yeah, I can hear you.
Oh yeah, I think Ahmad left.
Yeah, he might have lost his internet connection. I'm guessing he'll be back soon.
Oh yeah, I just seen suddenly like you are a host. Then I thought, what happened?
Has it got me as the host? Does it?
Okay, so let's continue on this formula now. So again, quickly, we have to design the connection or put connection in shear. So the shear force of the connection or the design shear of the connection, VF star, should be less than or equal to phi VF, where phi for the bolted connection is 0.8, was 0.9 for the tension member and compression member and flexion members. And VF is the nominal shear strength of the connection or of the bolts. The nominal bolt connection is given by the nominal bolt connection maximum shear is given by this formula, VF equal to 0.62 F ultimate F KR in AC NX and A naught. F ultimate F is the minimum tensile strength of the bolt based on the grade of the bolt, can be given from this table. This is F ultimate F. KR is a reduction factor given in table 9.3.2 to account for the length of a bolted lab connection. If the connection is not lab connection, so KR can be taken as 1. So we can also have a look on KR here. So if the connection lab length is less than 300 millimeter, so the K factor can be taken as 1. If the connection lab length is more than 1300, so it can be taken as 0.75. Okay, and if it is between 300 and 1300, it can be taken as this formula. If the connection is not lab connection, so can be taken as 1. So can take here for our calculation KR as 1. NN is the number of faces or number of shear planes with threads intercepting the shear plane. So we'd have drawn this bolt here, and we have part of the bolt is thread and the other part is a chunk. So for example, if we have 1, 2, 3. So if we have all this member, just an example. So how many faces through the thread? How many, sorry, planes through the shear planes mean number of shear planes. The shear planes between the connected plates. So number of shear planes through the thread is 1. So N in this case is 1. The other is NX, number of shear planes without thread interception. So we have 1, 2, and 3. So for example, here nx equal to 3. So this is the number of shear planes through thread and without thread. The other required parameter are AC, the minor diameter or the core area of the bolt, and so we have the core area and the nominal plane chunk area A naught. So A naught and AC can be found using this table based on the bolt size. So this is the core area and this is the chunk area. So This one A no C, and this one is A no AO. So if we know all these parameters, so we can find the nominal shear capacity VF, and then using VF we can know the ultimate capacity phi VF and compare it to the applied shear force on the connection FV. Sorry, VF star. So this one type of connection, when the connection, the bolted connection, the bolt is under shear. The other connection is bolt under tension. So the bolt in tension, a bolt subject to design tension force in TF star. So in this case, NTF star should be less than phi NTF. So NTF star is the applied tension force on the bolt. Should be less than or equal to phi NTF, where phi again is for bolts is 0.8, and NTF is the nominal tensile capacity of the bolt equal to area S, or the tensile area of the bolt, times FUF, where FUF again from this table is the ultimate tensile strength of the bolt, and AS is the tensile stress of the bolt, can be found depending on the size of the bolt from this column here. So this is the effective area and tension of the bolt. So 84.3, for example, for the M12 diameter bolt. Okay. So an example of the tension on the bolt connection. So if we have this type of connection here, for example, so might have few bolts here. So if we have a force here or a force here as well, so these forces will cause tension on the force on the bolts, or NTF or TNTF. Okay, so if this bolt is under tension, so NTF should be less than or equal to phi NTF, where NTF is equal to area S, the area of the bolt, times the ultimate strength of the bolt. In some cases, or most of the cases, we have bolted connection subjected to combined shear and tension. So you might have VF star and NTF star on the connection or in the bolt. So a bolt to require to resist both shear and tensile force at the same time shall satisfy the following formula for combined action. So V star F over phi VF all squared plus NTF star over phi NTF squared should be less than or equal to 1, where phi for bolted connection is 0.8. These are some design capacity summary given by some like bolts provider or some books. So for example, the maximum capacity of M12 in axial tension is 27 kilonewton. In shear is 15.1 kilonewton. And for class 8.8, there is no M12. There is M16 104 and 59.3. In brackets, single plane shear values for bolts with threads included in shear planes, and shear values in brackets are for bolts with threads excluded from the shear planes. So the values in brackets, if you exclude the threads in shear planes. Okay, and here is this is the snug tight bolt 8.8, and this is the tension bearing 8.8, and here is the tension friction 8.8. So this value can be used in like consultation design offices, so they can get the value directly from the table. But here in this course or in the problems, we need to follow the standard calculation to find the maximum capacity. So this values, all these values in the table just for reference, not to be used in our calculation. So another type of failure in the connection or in the bolted connection is bolt in bearing or crushing of the connected element, not the bolt itself. So crushing capacity of the play material subject to bolt bearing force V star B due to a bolt bearing due to a bolt in shear. So if we have something like this, and this is our bolt, so the bolt may cause a bearing on the hole here. So this is called bearing on the plate itself. So VB star should be less than 5 VB for the plate itself. Here we are for the plate or for the connected member. That's a Wi-Fi in this case is 0.9. VB is the nominal bearing capacity of a plate, which is equal to 3.2 dF dB F ultimate B, where dF is the bolt diameter, TB thickness of the plate. So if you have this is the plate, so this is TB, and the bolt diameter is dF. F ultimate B is the tensile strength of the plate or of the plate. Okay, so this is a failure mode of the connected plate, not the bolt itself. Another type of failure is the bolt tear out. So in this case, play may be tear out when in contact with the bolt. To prevent this, the bolt bearing force shall be satisfying V star B less than 5 VB. So it is very close to the previous formula, but the value of VB in this case will be different compared to the previous one. So in this case, as you can see here, due to the tension force on the bolt, so the bolt will tear out the plate and take this part out. So all this part will come out of the plate. Okay, so in this case, VB should be less than 5 VB. 5 here, 0.9 because it's for the plate. VB is the nominal Blee tear out capacity for a Blee in contact with the bolt equal to AE times TB times F ultimate B. So VB in this case equal to AE times TB times F ultimate B, where AE is the distance from the center of the bolt to the edge of the plea, minimum distance from the plea edge to the hole center in direction of bearing force. And what is TB? TB is the thickness of the plate again. And F ultimate B is the ultimate strength of the plea material. Tear out failure is usually more critical than bearing failure when AE is less than 3.2 dF. So if AE less than 3.2 df. So this means that tear out will come first, will occur first. Okay, this distance is common when standard end distance are used. So if you use the standard distance, so this will happen first. To overcome, a thicker blade can be used or add extra bolt. So as you can see, to increase this value, you need to increase this value, TB, increase thickness, or increase number of bolts. So the force is divided between 2 or 3 bolts. Another option is to increase the strength of the blade material. So if you use a stronger material, so it will be more stronger to resist the tear force or the tear out force. So these are few design criteria based on the failure mode of the bolts or the connected release. Connection components refer to clause 9.1.9. Connection components like cleats, gusset plates, brackets, which connecting the two elements together, the piece that connecting the two elements together, shall have their design capacity set for the following: connection component subject to shear, connection component subject to tension, so shear or tension or compression, connection component subject to bending, or finally block shear capacity for connection component member framing into connection components. So these are the modes of failure for the component itself. So again, up to here, we were designing the bolts. For example, if we have this two in plan, so we have designed or checked the bolt and checked the two be connected together. In some connection, similar to the beam to column connection, for example, we need to have a cleat. So we need the next now is to design the connection component. How to design this connection component? So we need to check it for shear or tension, compression, bending, and block shear failure based on what is the applied action on this connection or in this component. So let's look at design of shear capacity of the connection component. So the shear capacity of the connection component, similar to this plate here. So since shear distribution in a rectangular cross section is non-uniform, design shear capacity of plate should fulfill the following. Phi VF should be more than V star, or V star should be less than phi VV, where V star is the applied shear and phi VF is the strength or the shear strength of the component. So for example here, if we have this component here, so the applied shear is this force VF, V star, sorry, should be less than the strength of this plate. The strength of this plate here will come using this formula. VV equal to 2VU divided by 0.9 plus V star VM over V star VA less than VU. So the maximum value of VV is VU, where phi is 0.9. VU is the nominal shear capacity of the web with a uniform shear stress distribution. So VU is the nominal shear capacity of the web, where V star VM is the maximum design shear stress in web, equal to V star Q divided by IT. V star VA is the average design shear stress in the web, both determined by rational analysis, or equal to V star over dt. So we have VM and VVA. One of them is the maximum shear, design shear, and one is the average. The maximum design shear is equal to the applied shear multiplied by Q over IT. The average is V star over dt. So this is the two values required, and T is the thickness of the plate or thickness of the component. For a rectangular section which would be used, you can use VV as the following. So you can ignore this one and focus on this one. So for rectangular section, similar to this one here, this is the rectangular section. So you have D is the depth, T is the thickness. So VU will be equal to VW 0.6 F yield times DT. So if you want to check the shear for this plate, you need to find VU from here, put VU here. Okay, and find VV. Then using VV, you can check V star. For block shear failure or block shear capacity of the connection, the block shear failure through a group of bolts hole at a free edge should be prevented by checking the design shear or tension force R star BS. So similar to before, if you have group of bolts here, so it might shear like this and lift the member. So all of this part will be removed and the remaining will be only this part like that. So this is called block shear failure, and we need to check the capacity against the block shear failure R star BS less than or equal to phi RBS, where phi is 0.75 here for this block shear failure. RBS is the nominal design capacity in block shear and is given by these two formulas: 0.6 FUC ANV plus KBS FUC times ANT, and should be less than or equal to 0.6 FYC AGV plus KBS FUC ANT, where FUC is the minimum tensile strength of the connection element. So the capacity of the tensile strength capacity of the plate. FYC is the yield strength of the plate. ANV is the net area subject to shear rupture. ANT is the net area subject to tension or at rupture. AGV is the gross area subject to shear at rupture. And KBS is a factor to account for the effect of eccentricity on the block shear capacity, equal to 1 when tension stress is uniform, 0.5 is if the tension stress is not uniform. So let's look at this examples here for block shear failure. So for example here, if we have this example here, so we have the shear force or the RBS star. So this is the shear force causing block shear failure. Okay, so if we look at the areas here, we have area parallel to the force, this blue areas. So this areas or area NV parallel to the force. This area is shear area. There is another area perpendicular to the force here. So this red area will be under tension or area NT perpendicular to the force. That's why this is a tension area. So there is two types of stresses in this case, shear and tension. The shear area again is the blue one, parallel to the force, that's why it is shear. And the other one is the perpendicular to the force or the tension ones. Okay, so if we return back to the formula, we have two parts of the formula. We have the first part is for shear, the second part is for tension. So this is the strength against block shear failure. So half or part for shear, part for tension. The last part is if we have group of bolts and we need to design the group as they working together. So strength of a bolt group according to clause 9.4, connection consists of minimum of 2 bolts and often more than 8 bolts known as bolt group. So you can design a bolt group starting from 2, but usually more than 8 are considered as a group. But if you want, you can consider from 2 as a group. A bolt group may be acted on by loose bending moments in plane of bolts in plane at right angle to it out of plane loading. So we can have in plane loading and out of plane loading on the bolt group connection. For example, in plane, this example here, so we have this force here, and these are the bolts we have. So in this case, this force will be divided to these groups, and because this force will cause moment, so each bolt will take a force and a moment from this load. And as you can see, the bolt is in direct shear and torsion. That's why it is in plane. So if this is the plane of the force, so the bolts are in the same plane of the force. That's why it is called in plane. Okay, but if you look at this example here, so we have the bolts in this direction. So here in this case, if we have this force will be divided to these bolts here. So the force here will be perpendicular to the bolts. So if this plane of the force, so the bolts are out of plane or in other plane here. So they are not in same plane. That's why it is out of plane loading. And these bolts are in under shear, will be under shear from this force. And also due to the moment, this force will cause moment. Due to this moment, some of these bolts will be under tension, some of them will be under compression. So these bolts will be under tension and shear. Here, this bolt here will be under shear and torsion. So if the group in blank group, so the bolts will be under shear and torsion. If it is out plane group, so the bolts will be under shear and tension. So forces from group designed action effects acting on individual bolts are proportional to the distance from the bolt to the instantaneous center of rotation ICR. So each bolt, we have a center of rotation called ICR. So each bolt will take a proportion or percentage from the load based on its distance from the bolt, to the center, to this center. So we have this center to here. So for example, this is the maximum distance. So that's why this bolt or this bolt or this bolt, these 4 bolts will take the maximum force. But those bolts, for example, will take less loads because it is less far from the center. So the idea here is based on the distance from the center to the bolt. Critical bolt, the fastest one from ICR, will be subjected to the greatest shear force arising from combined effects from overall bolt group design action. Critical bolt is then used for design check of the overall bolt group. So when designing, we design only the bolt with the maximum force, which would be the farthest farthest one, farthest bolt from ICR. Okay, so this is the idea behind the group of bolts. Let's look at the in-plane loading, the theory behind assumption. Rigid connection. So the assumption is we have rigid connection. Why we have rigid connection in this type of bolt design? Because we have moment. So if we have moment, so the connection need to be rigid. With pure couple, ICR coincide with the centroid of the bolt group. And with in-plane shear force, no eccentricity, ICR is at infinity, so that design shear force is uniformly distributed throughout the bolts. Superposition is also applicable in this type of bolts or in this type of design. So let's look at the example here to the left here, group geometry and loading. So if we have a force here with eccentricity, so we have a centroid of the group bolt. So if you have this 6 bolt group, so the centroid would be somewhere here. So this is our centroid and this is our bolts. So if you need to design this bolt, so we have a force here. So there is no problem with this force. But the problem is that we have due to the eccentricity Ex. So we need to have, or we will have a moment M star equal to Vy star times Ex. So we will have M star and Vy star applied to this group. Okay, and also we have Vx. So we have another force Vx star. This is a general case. In some cases, we don't have all of them together, but this is just a general or the general case if we have two shear at the same time. So you need to distribute the moment Vf and Vx on all of them. So you will have to use this formula here to find the resultant force. So if we have a general case of Vm, V star, Vy star, Vx star, M star, so the resultant force will be the root of Vy star over N plus Mi star time X max over Ib all squared plus Vx star over N plus Mi star Miy max over Ib all squared. Okay, so from the given data we have, we know V is the given Vy star is the given value of shear in Y. Vx star is the given value of shear in X. Mi star is the given moment or the moment we got. So Mi star equal to Vy star times Ex, for example. So Mi is given. What is X max and what is Y max? If you look here, X max and Y max, X max is the maximum X for bolts from the centroid. Y max is the max Y for bolts from the centroid. So for example here, what is the first X? So this is the first X, if this is the centroid. So all of them are at same distance. So this will be xn or x max for us here. What is y max? We have y for this one 0, y for this one is yn, so this yn will be y max. N is the number of bolts, so n number of bolts, which is 6 in this case. And IB is equal to IY plus IY, where Ix is equal to summation x n squared, Iy summation y n squared. So we have 1, 1, 1, 1, all of this same x and same y, and 2, 2. So for example here, if I write x1 will be, let's say xn, because it's given as xn, there is no number here. And x2 also same x, so xn. Y1 equal to yn, y2 is equal to 0. So if you sum for this 6 bolts, xn and yn squared, so you can find IB. So you know n, you know IB, you know n, you know IB, so you can find the resultant force for each bolt. So this will be the maximum resultant force. We need to check for the bolts, and we can directly use the formula. So this is just explanation that each bolt will take its proportion from the x force, its proportion from the y force, and a value of Fm. Fm is a force due to the applied moment. So we just need to use a final formula, which is Va resultant star equal to this formula. So the application of the bolt in plane to identify by inspection the bolt with the largest resultant force, normally the farthest away from center of the bolt. Label all the forces and calculate the resultant. So the resultant will be as that. So N number of bolts, Vy, Vx applied force, Mi is the moment applied from eccentric shear force, Yx and Ymax and Xmax is the maximum distance from the centroid to the farthest corner bolts. Check V resultant star against the shear and bearing capacity of the bolt. So the idea is for a group, we find F star resultant compared to phi V or phi VF, depend on the type of force. For the out of plane group, remember? So we have again theory and application. So some bolts positioned in the bearing compression, part of the connection are not loaded. So for this type of connection, like similar to this one here, so we have V not star and E. So again, we will have a moment. But this moment will be transferred to the bolt as two type of forces, tension and compression. So part of the bolts will be under tension, for example, the top two, and some of them will be under compression. So in this case, some of the bolts are under tension and some under compression or bearing. And if some bolts in the middle, so will be under no forces. Okay, so forces in tension region can be evaluated by assuming a linear distribution from force from the neutral axis. The neutral axis assumed to be positioned at d/6 from the bottom of the end plate. The first bolts are more critically loaded bolts with total tension T1. So as you can see here, we convert the moment to this type of stress. So the maximum forces would be at the farthest bolt on the top again. So that's what we are designing. So this is just the theory behind the methods, but now we can just go to the application. So we have two application, exact application and simplified application. So we will work directly on the simplified one. We don't need to go through the exact one. For simplicity, we will be using the approximate method of analysis for finding the maximum force. So if we have a group of bolts, for example, 4, and we have V star O. So the moment on this, and this is EX. So the applied moment here, in this case, M star will be VO star times EX again. So we will have some assumption that the center of the rotation at the bottom bolt, so Yn is 0. Ignore the contribution from the compression, so Yc equal to 0. Load varies linearly from bottom of the bolt with maximum load T1 in top bolt at distance Y1. So the maximum tension in the bolt T1 at the top bolt will be equal to M star O, this one here, times Y1. Y1 is the distance to the highest bolt or to the top bolt over summation yi squared. So this will be the method we will be using. So for example here, sorry, just so y1 will start from the bottom bolt to the top bolt. So the distance from here to here is y1. So for example, if we have this example here, so we have 1, 2, 3, 4, 5 bolts. So y1 starting from the bottom bolt to the top bolt here. So this is y1. So T1 is the maximum force. T1 will be MO star times Y1 divided by summation YI squared. So if this 1, 2, 3, 4, 5, so we have Y1, Y2, Y3, Y4, and Y5. So this group of bolts will be subjected to two things, T1 and VO star. Okay, so the force on the bolts will be divided. These two forces will be divided between this group. So if we have the side view, so if they are two rows or two lines, so we have to subdivide the forces between them. So for the top ones, or for the bolts, T1 over N1, and for shear it is V star V O star over N. So T1 will be distributed over the rows, and V O star will be distributed over the bolts. Okay. So for example here, N1 is 4 rows and N is 8 bolts. So you will find T1 and V star. So each bolt will take T1 over 4 and V star O over 8. So this is the design forces on the bolts. And in this case, the interaction equation should be used for combined shear and tension because we have tension and shear. So in this case, we have tension force T over 4 and shear force V star over 8. Then you can check and find the forces and find if it is safe or not, safe design or not. Okay. Do you have any question, guys, regarding the groups, the bolt groups?
No, sir.
Only portfolio?
Sorry, I couldn't hear you. Can you repeat it?
Is it only portfolio left for this unit?
Yes, assessment 3 is the last one.
Yeah, it's
And
the
I
last one.
will, the marks of assessment 2 will be released tomorrow morning. So
Nice, thank you.
you just have to complete assessment 3 and that's it. And as you have, I'm recording a video to clarify some points in the assessment 3, and they will be
Yeah.
posted tomorrow.
Okay, great. Thanks.
No worries. Do you have any
also-
question, guys, about regarding the assessment so that I can add to the video? Or
I was just wondering if you could include either some information on how to use space gas or maybe
yeah,
just some
sure.
links or
This is
something.
mainly for
Yeah.
that. So I will try to record, add a video on how to model and run the model on space gas through this video.
Yeah. Oh, that'd be great. Yeah. Thank you.
No worries.
I'm using strand 7 for the assignment. Was that okay?
Yeah, sure. If you have a license to strand 7, it's okay as well. But both
Yeah.
of them will give almost same. But the idea is just to include some software or finite element software to check the moment and shear and so on. So it is mainly for moment and shear and normal force diagram.
Yeah, so you want us to do those by hand, roughly, and by the software?
Yeah. The idea is all the calculation should be manually, but just you need to add draw the model and add the loads on the software and run, so that to make sure the bending moment diagram and shear force diagram are correct.
Sure.
Okay. Okay, so I will try to post this tomorrow as soon as possible so that you can have a look on it.
Thank you.
No worries, thank you. Okay, so this is also the tutorial example. Do you want to go to have a try in one of the example, and I will try to help you if you have any question, guys. So for example, this example number 2, can you have a try on it on this one?
Sure.
There is one for the double shear lap joint or the connection under bolts under shear, and there is one for in-plane group member, so can have a look on this too, and I am here to help you. Okay.
Hey, Ahmed, do you think you could go through example 2? Just might be easier because sometimes going through the formulas where things aren't written, it's sometimes a bit hard to follow what's going on.
Okay,
Sorry,
no
going through
worries.
the solutions. Yeah, that'd be good. Just
Okay, no
He's sort of
worries.
explaining. Yep, thanks.
Okay, all right. So I can do. Can you see the screen?
Yep,
Yeah. Okay. So if we look at this example here,
yep.
so we have double shear lap joint carry 1,000 kilonewton. So we have 1,000 kilonewton from this side and 1,000 from this side, and we have 6 millimeter plate. So these two plates are 6 millimeter each, and the thick one here is 10 millimeter. So we need to design the double shear joint and provide the edge pitch and edge distance detail. So in this example, we use like M20 4.6S bolt, and the shear capacity of the bolts. So if we look at the connection in plan, this would be the connection in plan,
So,
for
so
example.
to get the bolts, do you just guess that? Is that
Yes, because the details of the bolts are not
not
given.
given?
Yes,
So just have a guess and see if it works.
yes.
Okay.
But if the details of the connection is given, so you work on that. But here it is not given.
Yeah.
So there will be some bolts here. So, but actually it is one. So maybe just adjust this. Because it is only one line. Okay, so we have 1,000 here and 1,000 kilonewton here. So shear capacity of the bolts, V ultimate, so phi VF, where VF is equal to this formula here. So phi is 0.8, this formula 0.62. FUF is 400 MBA for this type of bolt, 4.6. KR taken as 1. NN is how many plates in the threads and how many plates in the shank itself. So assume this as 1 and this as 1. So we take this one and this is 1 here. So AC and A note are taken from the table. So for M20, there is also tables for the bolts. So M20, AC and AO is 225 and 314 millimeter square and millimeter square. So the capacity of each bolt is 106.94 kilonewton. So here, assuming that thread intersecting one shear plane. So how many required number of bolts? If one the maximum carried by one is 107. So how many bolts number of bolts required will be 1,000 over 106.9. So we need at least 9.35 bolts. So we round it up to 10 bolts. So we need 10 bolts for this one. So the force per bolt will be 1,000 over 10 volts, so 100 kilonewton. Okay. So do you understand up to here? So because the number of bolt was missing or not given, so that's why we need to get how many bolts. To get how many bolts needed, what we did, we get the maximum capacity for each one of the given one here, which is M20 4.6/S grade. So the maximum capacity for each one is almost 17 kilonewton. So the number of bolt will be 1,000 the force, the total force over 107. So give us almost 10 bolts. So you will need at least 10 bolts to carry this shear force. Okay, for the arrangement of the connection, we need to find how many or how much is the minimum pitch and how much is the maximum pitch and how much is the edge distance. So for plate 6 mm plate, because we have 10 mm and 6 mm, so which one would be critical? The 6 mm ones or the smallest one. So the minimum pitch is 2.5 df. So the minimum pitch is 50 mm. The maximum pitch is 15 T plate. So it is 90 mm. The minimum edge is 1.25 T plate, so 25 mm. The maximum edge is 12 T plate, so it is 72 mm. So it was taken as the pitch distance 50 mm, the edge distance as 30 mm. Okay, so just take 50 and 30 between 25 and 72. So this for the bolts itself, the number of bolts and the number of the pitch and so on. Then we need to check the bearing capacity of the plates. Is there any tension force on this bolts? Because we designed the bolts itself for tension or shear. So this bolts only under shear or under tension and shear? Do you have any idea?
Is it just shear?
Yeah, that's shear. So these bolts are only under shear. That's why for the bolts itself, we check the shear and find the number of bolts. But then we need to check the two or the play connected to this connection. So we need to check these two criteria, the bearing capacity and the tear out capacity. So for the bearing capacity, 5 VB, where VB is 3.2 DF T plate FU ultimate B. So for the 10 mm plate, 5 VB 0.95, 3.2 DF is 20, TB 10 mm, FUB is 410. So it is 32, sorry, 236. And 266 is 5 VB for this plate. So for the 10 mm plate, 5 VB is equal to 236. So this plate will tear out at 236. What is the force we have on this plate? 1000. So is it safe or not safe?
Not safe.
No safe, because VB is the applied force. So VB star is equal to 1000. So we are doing the
Oh,
reverse
yeah.
here, William. So
Oh, yeah, yeah.
we got the
Sorry.
capacity. Yeah, no worries. Here is 1,100, sorry. How much is the force? 100? I'm sorry. So one side here is it 1,000 or there is a typo here, I think. Okay, just a second, guys. So for the 10 mm plate, so 0.9 times 3.2 times 20 is 10.
maybe it's where you've got is it per bolt? Because you've got 10 bolts. So you're dividing it by
Yeah,
10.
yeah, you're right. So this 1000 bare bolts. So sorry, 1000 over 10. So it is 100 kilonewton. That's why it is okay. So because we are checking bare bolt, not for the hole, because the bearing will happen if this our bolt and we are tensioning from here. So the bearing will happen bare bolt, not for the whole force. You're right, William. Thank you. So this force is bare bolt. That's why it is okay. Okay, so this is the capacity and this is the applied force. So if the capacity more than the applied force, is it safe or not? Safe. Can you hear me, guys, or was I just lost? No, is the
Yep, no,
connection
it's
there?
all,
Yeah.
that's
Okay.
all good.
Okay. For the 6 millimeters blade, same formula. But what is the thickness of the blade here? 6. So the blade capacity for bearing is 141. What is the force per bolt in this case? 50 kilonewtons. So is it safe or not? Safe.
Yep, safe.
Yeah. So that's why this condition is safe. For tear out, the tear out is different formula. So VB equal to AE times TB FUB. What is the edge distance we selected here? 30 millimeter. So if you go back to the previous or the original lecture, so this was AE. So AE is the edge distance. We assume it as 30 millimeter. So for the 10 millimeter plate, 0.9 is phi, 30 is the edge distance, 10 is the thickness of the plate, FUB is the ultimate strength, 110, more than 100 kilonewton per bolt. So it is okay. For the 6 millimeter, so same, but just the blade thickness is different, and we compare to 50, so both of them are okay. So the connection design is satisfactory. Okay. Is it okay for this example?
Yep, thank you.
No worries. So let's go to have another look here. Take this one. So this example is for bolt group in plane. So we need to determine the adequacy of the bolts on the shown bracket. Grade 300 steel, M20 2.8/S bolts in single shear. This is an eccentric connection with the action load in the plane of the bolts. Action is eccentric to the centroid of the bolts. So this is a clear example that we have a connection, in plane connection. As you can see here, the force is in the plane of the group bolts. We have 6 bolts here. So the centroid of this bolt, where is the centroid of this bolt? Here is the centroid, CG. Sorry, here is the centroid. The eccentricity is given and the force is given, everything is given here. So that design force is 120 kilonewton. Eccentricity to the bolt group is 300 millimeter. The bracket is 250 broad flange or parallel flange channel, grade 300. Thickness of the bracket web is 8 millimeter. The column size is 250 UC. Thickness of the flange 17.3. Width of the flange 256. Edge distance to edge of flange is 48 millimeter. Tensile strength is 440. Okay, so first of all, we need to find what is the design action on the bolt group, M star and V star. So V star given to us as 120 kilonewton. Do we have any horizontal shear? We have only Vy star 120 kilonewton. For M star equal to the force times E. How much E? 300 millimeters, so 0.3 meters, so it become 36 kilonewton meter. Okay, so actually we have for this connection, if we have this is our connection, so we have 120 kilonewton here, and we have 36 kilonewton meter. So the first step is to find the polar moment of inertia, IB, for the group. How to find IB? IB is summation x, y for each bolt. So what is x for each bolt? All of them 80. What is y? 4 of them has 90 and 2 of them has 0. So if I ask you how much IB, so it will be 6 bolts times 80 square. So this is summation x squared. Are you okay with this one? Because all of them is, if this our origin, 0 and 0, so all of them 80. Plus for summation y square, we have 2 times 0 plus 4 times 90 squared. Is that correct? So this 4 has 90, this 2 has 0. So it is total 70,800 millimeter squared. Okay, are you okay with this one? So this is the required data. So now we apply in this formula. If you remember this formula, so V resultant star, which is the maximum shear on bolts on the first bolt. Which one you expect is the first bolt? You, according to our drawing here, all this corner will have the maximum shear forces. So if we apply this formula, do we need the two terms or only one of them? So we have value of Vy and My times x, but Vx is 0, right? So we don't need this term. So V resultant will be 120 V times 10 to the power 3 to make all the units in Newton and millimeter. Because we have I in millimeter, so to be careful with that. So we have number of bolts 6. So this will be under the root. So plus, and we have another bracket here. So this is the first term, plus Mi is 36 to the power 6, because to convert to Newton millimeter, times 90, which is x max. So x max, how much x max? X max is 80, so might be something wrong here. So this one should be 80. So times 80 over IB. How much IB? 70,800. So all of this under the root, and this is squared, plus Vx over n is 0 because there is no Vx, plus mi 36 to the power 10, sorry, 36 times 10 to the power 6 times y max is 90 over 70,800 all squared under the root. So we can find V resultant star. So it will be not this value. Can you help me to get this value? Any of you? Just to confirm the.
I think that should be right because you had 90 and 80. It's just you've swapped them around, the X and the Y.
Yeah, so yeah, but I mean, if you, it will be gives the same value. You think so?
I think it should do.
Yeah, because there is no multiplication or summation, so it's all of them under the same root. So you are right, but just this need to be here and this to need to be here. So the value will be 76 kilonewton. So the maximum shear on this on the first bolt will be 76 kilonewton. So after we get the resultant force, so it will be similar to what we have done in the previous example. So we have bolt under shear. So the shear capacity of the bolt is Vf equal to 0.8 phi 0.62 Fu F or F ultimate F. Why it is 830? Because the bolt is 8.8. Kr take as 1. Nn is 0. So we assume there is no threads in the no shear planes in the thread, only one shear plate in the chunk. So A node is 314 over 1000. So this give us the capacity of each bolt is 66.2. So I think I changed the calculation again. 0.8 times 0.62 times 830 times 3. Okay, so this value is 129.27. Okay, so just as a typo here, so remove this one. So how much is the capacity of the bolt? 129. How much is the applied force? 76. So it is safe or not safe? Safe. Okay. So what we need to do again, find the resultant force compared to phi VF. So if phi VF more than V star, so this is okay. So again, this is a bolt. There is no tension on this bolt, so we need to check the capacity, the bearing capacity and the tearing capacity of the bolt, of the blade, sorry. So the bearing capacity of the blade 3.2 DFTB FUB. So 0.9, 3.2, the diameter is 20. T blade is 8 millimeters. This was given. 440 is the ultimate strength of the blade. So the capacity is 202, more than the applied force, so it is okay. So if we look back here, so the bracket thickness was given as 8 millimeter. Okay, so that's why we check the 8 millimeter and it's okay. So for the blade tearing capacity, So same, but just AE is the edge distance times TB times FUB. So for the edge distance for the web, how much edge distance for the web? So this is AE for the web. So AE for the web was 90. For the edge distance, we take the edge distance as 48 millimeter. How we get this one here? So we get B flange minus 2 times 80. Okay, so how can we find AE, AE, guys? Do you know?
No, I'm not sure.
Okay, so this is the flange of the column. So the bracket is connected to this column 200 UC. So if this is the flange width, so the flange width of the UC is given as 256. So we have here AE, this is the distance AE, and we have here is 80 millimeter. So AE will be 256 is the total flange minus 280 minus 2 times 80, because we have one from this side and one from this side, over 2. So this give us AE, or the edge distance, as 48 millimeter. So AE was taken as AE as 48 millimeter. So phi, or tearing distance, would be 0.9 times 48 EE. TB is the blade thickness. 440 is the FUB. So it give us the value of 152 kilonewton for the bearing, the tearing capacity of the blade, more than the applied force 76, so it is okay. So the group, the 6 M20 over 2.8 snug tight bolts are adequate, or are satisfactory, because it satisfy all the conditions. Okay. Do you have any question, guys?
No, I'm all good, thanks.
All good? Okay, thank you. So this is another example of the groups. So you can have a look on them, and if you need any questions, just let me know, guys. Okay. Okay, well, I will upload the video, recording of this video on the course website, and when I complete the other video, I will also maybe send you a notification or something that I have uploaded to the course website. Okay, do you have any question, guys? Do you have any problem with the marking of assessment 1? or the marks.
I've just got a quick couple of questions on assessment 3.
Okay, no worries. Go ahead.
Just firstly, just the with the section view of the parking shed, that's just a cantilevered beam, isn't it? It's not like half of the structure. That's the whole structure. Is that
Yeah,
right?
this is section view only, like because I just try to like simplify the calculation. So
Yeah.
I give
Yep.
you the calculation directly. So what you need to do is just find the load combination. So we'll
Yep.
find a maximum load, uniform load on the beam, and the load on the column will stay same, 2 kilonewton per meter.
Yep.
So then you can just start like determine the reaction and the bending moment and so on, and
Yep.
then design the rafter for the moment and shear, and
Yep.
design the column for moment and normal force,
Yep.
and
Okay.
design the connection. So it's just like because we already have done the wind calculation and dead load life load calculation for assessment 1, so there is no need to do it again in assessment 3. So what you
Oh,
need
the
to
wind.
do, yeah, so there is no calculation for any loads. The loads are given to you directly. That's why no need for plan or other views.
Oh, okay. So we don't need to do the load combinations, as in
Yeah,
like
like
factoring in.
1.2 G
Yeah.
plus
Yep.
1.5 Q plus W. So this would be the load combination on the rafter, and because
Yep.
the column has only wind load, so it will stay 2.
Yeah. Okay. Yeah. All right. That's
Then
cool.
using the structure analysis, like find the reactions and the road shear force diagram and the moment diagram,
Yeah.
and check
I just
with space gas.
Yeah. Okay. With the load combinations too, because we generally calculate them in like kilonewtons per meter. With the point load, do you divide that over the distance of the
Where is the point load? There's a point load at the edge, right?
at the edge? Yeah.
Yeah.
So would you divide that by the length of the
No, just
member
to
to
keep it
get?
like this. Just to keep it like that.
So you just keep it. Okay.
Because the load combination, they doesn't need to be summed together. So just mean that if you have several loads together, like from several type, like you cannot add point load to inform load, but you can add uniform load together. So like for this example
Oh
or this
yeah.
problem, you have wind load, dead load, life load. So you can combine them in one combination. But if you have point load, like for example, it is from dead load and live load. So what is the combination of this one? 1.2 G plus 1.5 Q. So this is how to combine that. But there is no need to combine the point load and uniform load together.
Okay.
So for example, if we have 1 point load G for dead load and 2 point load for Q. So the total load or the combined load will be 1.2 times 1 plus
Yeah.
1.2, plus 2 times 1.5. So it will be 1.2 plus 1.5 times 2. So the total will be 4.2 kilonewton as a point load.
As a point load, yeah.
Yeah, so the point load will stay point load, but just combined,
Oh, okay. Yeah.
the
Yep.
uniform
Yep.
load will stay as a
So
uniform load, but just combined. But you
yeah, I
can
get you.
you don't
Yep.
have to like distribute the point
Yeah.
load again
Yep.
or
Yep. No.
concentrate the uniform
Yeah.
load again.
Yeah. Okay. And then just with the combined loads, then you can apply that
Yeah, so the
whatever
idea
you've
is
figured
just
out for the.
find the
Yep.
maximum load as one uniform load on rafter, 1 point load
Yep.
on rafter,
Yep.
and the 2 kilonewton stay as it is on the column.
Yeah. Yep.
Then
Okay. Yeah.
yeah,
That's makes sense. Yeah.
yeah. As a simple like or as a frame analysis in any structure course you got, you can find the reaction and
Yeah.
draw the bending moment and shear force diagram.
Okay. Yep.
So I already have like I will summarize this in the video. and show
Okay,
you
yeah.
how what is the final view of the requirement.
Yeah, that'd be great. Yeah, no, that helps because I was having trouble getting started because I was just unclear on the loads. Once I know the loads, it's a lot easier to start working away. So
Yeah, no worries. Yeah, the idea is
that's good.
after you get the bending moment, so it will be similar to like the normal procedure. So just to get the maximum moment on the rafter and use it to design the rafter and the column and so on.
Yeah. Okay, great. Thank you.
Okay, no worries. Well, okay, guys. Any other question today?
Oh, good, thanks.
No worries, guys. Thank you, and thank you for attending the whole semester, and hopefully see you again in different course or any other course.
Thank you so much, Ahmed, for today
Th-
and all the classes.
Thank you, Bash. So I
Yeah,
couldn't
thanks.
hear somebody was talking, but I couldn't hear him. Thanks. Well, go ahead. Sorry
Thanks,
for
Ahmed.
disturbing you.
Yep. No worries.
Thank you,
See you
guys.
soon.
Thank you.
Bye.
See you. See you. Bye.
Thank you. Bye.
Thank you. Bye. Have a good night, guys.
You too. Thanks.